So it's interesting, modern physics. But I will start with recalling basic properties of a very classical physics, or actually a field that was developed, initiated by Maxwell, Faraday, and many others. So actually we start to consider or reconsider the equations that were known in 1860, more or less. Why equations of 1860 in modern physics? Well, I will show you why. And I can anticipate the meaning of doing this. The meaning of doing this is to rethink, re-understand what was developed more than 100 years ago in terms now of a topological approach to field theory. Topological meaning continuous deformation of the fluid, of the system, and interpretation of some quantities that are invariant during the fluid motion in terms of topology. Okay? So please stop me if you do not understand my English. Okay? I cannot speak Chinese, sorry. So you ask me, what do you mean? Okay, you stop me and you ask, what do you mean? Right? All right, so as a kind of subtitle, I will write again what Professor Liu just mentioned. So we start considering ideal magnetohydrodynamics. What is this? Ideal, no dissipation. Magneto, meaning magnetic fields. The presence of magnetic fields, and the magnetic fields are transported by fluid equations. Okay? So this is the context. I introduce this and we move to the concept of magnetic helicity. This is something new, introduced more or less, 1960, and only now starts to be discussed in textbooks. You will understand why it's important. From this, for today, we stop here. Okay? So today we cover these aspects. Next time that we meet, I will tell you something about Ampère. Ampère's theorem. Again, Ampère. If here magnetohydrodynamics brings you back to 1860, and from roughly 1860, we get to here 1960, more or less. Same story here. We start from roughly 1830 Ampère, and from Ampère we get to what I said, linking number. Linking number means from these years, well, is an interpretation of magnetic helicity. We get to 1970, more or less. Okay? So this is first part, and this is second part. Okay? So today we cover the first part. Linking number, it is interesting because linking number is a fundamental invariant of topology, and it was introduced in literature by Gauss. And so we are same year, more or less, 1830, 1833. And from there, we get to the modern interpretation of linking number. So, in other words, from the last part of last century. So this is the plan of the lectures. You see, we start in both parts from the old work of field theory, and we get to the modern interpretation of field theory in terms of topology. Okay? This is the plan. All right. So let me start from ideal magnetohydrodynamics. And very often this is called ideal MHD, magnetohydrodynamics H and dynamics D. Okay, ideal MHD. Okay, so in order to understand what we are talking about, I will recall basic equations of the fluid motion. Okay, so from fluid dynamics, we have two equations. First equation, transport conservation of mass. It's a conservation law. It means the mass of the fluid is conserved. I just do not derive this equation. I give it for granted. It's a well-known equation. So we just write it down. It's just a derivative, partial derivative of density rho with respect to time. And this balance is changed by the divergence of the density times the velocity. Okay, so rho is a fluid density. U is a vector, so this is equivalent to write something like this, and this is the velocity field. The velocity field is the velocity with which fluid particles move in the fluid. Okay? Density and velocity. And this equation is set to 0 because there is a balance of mass transported by the velocity. This equation is the differential form, is a local form of a general principle of conservation of mass. Okay, this is the first equation. We have a second equation. Second equation is conservation of what we call linear momentum. Linear momentum. So we balance Newton's law. We balance forces, mass times acceleration, with the forces in order to have a balance between the motion due to mass times acceleration and the forces that induce this motion. So this is given by the Lagrangian derivative of the velocity d dt Lagrange derivative. And what is this Lagrangian derivative? Is the sum of two quantities. One is the Eulerian derivative, d dt, change in time of some quantity, plus the u dot grad of something, and this is the space derivative of something, because this grad operator is d dx, d dy, and d dz, x, y, z being our coordinates in R3. So there is a change in time plus a change in space, and the sum of these two gives you the total change. And is a total change of u in time. What does it mean? It means as an acceleration. The fluid accelerate, du dt, acceleration, times the mass times acceleration, that is a force, and we equate this force with the forces that are present in the fluid. Which forces are present in the fluid? Well, one force is the difference in pressure. So this is minus grad of P. So P, pressure. I give you a physical intuition of this force. Suppose in this room we open a window. When we open a window, we feel a flow of air that goes from the window to the door. That flow of air is the force that pushes the fluid from one place to another in the room. Why there is a minus? Because we go from high pressure to low pressure. So this is the force due to pressure. Okay, so far, if we stop here, we are in ideal situation. What does it mean, ideal? It means no dissipation. It means no viscosity. What we have at the beginning is what we have at the end. No dissipation means also no entropy production. Okay? So this is the set of equations. We can call these equations, exactly these, are the Euler equations. Okay? Now, are these Euler's equations what we have now today? Of course not. Of course not, because after so many years, from 18th centuries to today, a lot of progress has been done. People studied viscosity, viscous effects. So if we want to improve this equation into modern terms, we have here to add viscosity times the Laplacian of the velocity field, and maybe something else. If we go to increase complexity, we are going to equations that are called Navier-Stokes equations. Okay? And then Navier-Stokes equations are these ones, with viscosity, etc. But today, we want to be even more complicated. Not good idea to be more complicated. I work in applied mathematics, and mathematics want things to be simple, not too complicated. But just for reference, I put magnetic fields in it. So I have to go on and to add here something else due to the presence of magnetic fields. Okay, magnetic fields now. Magnetic fields, so I will refer to the magnetic field B. So this is the magnetic field. And when I introduce magnetic fields, usually these are coupled with electric field. Electric field. And we are at the time, at the very beginning, around here, more or less here. So we have Maxwell's equations. Maxwell's equation. So I will introduce Maxwell's equation to you in a very, very simple form. In other words, I will not care, my mistake, I will not care about some physical coefficients that are important, of course. I want you to focus only on the formal, the mathematical relations between various components, okay? So I will not mention too many coefficients. So one form of Maxwell's equation is the following. We have, first equation is that the electric field generates from somewhere. From where? Electrons. So the divergence of the electric field is related to rho e, the mass of the electron. And then, associated with the E, we have the transport of E, of the electric field, and this is time derivative of E equals the curl of B, the curl of the magnetic field, and there's a minus current, okay? J stands for current density, okay? So this is the first two equations that are related to Maxwell's work. And there is another two equations. First is the divergence of B. Divergence of B. Where is the origin of a magnetic field? Today, till now, we do not have evidence of sources of magnetic fields. Of course, you can do a theory about that, but in terms of experimental evidence, we do not have proof of existence of sources. Here we have the electric field, the source is the electron. Here we have a magnetic field, the source is not known. We don't know about the existence of magnetic monopoles. So we set this quantity to 0. Okay, absence of magnetic poles, and then we have a transport equation for the magnetic field. So we have dB, dt, and this is just a minus curl of E. So these equations are Maxwell's. Okay? If we have these equations, presence of magnetic field, I'm afraid we have to add to the Navier-Stokes equation the presence of magnetic field. And we have a constitutive law, i.e. an equation that is due to experience. We have to accept it. We do experiment, we compute things, we relate one thing to another. And the constitutive law I'm referring to is Ohm's law. What does the Ohm's law say? Okay, it says that eta times the current due to conduction is equal to the field E plus the combination of U with the magnetic field. So this is an additional law that we have with this. Wow, so many equations. Continuity equation, conservation of mass, okay. The motion of the fluid controlled by this force and balanced by these forces. And here we have to put the magnetic field contribution. I didn't write it. If I put the magnetic field contribution here, I have the equations of magnetohydrodynamics. Hydrodynamics given by the Navier-Stokes equation plus the presence of magnetic field here. Magnetohydrodynamics. To solve this equation, very complicated. Okay, so this is the beginning of the story, but I don't want to make it so complicated. Why? Is any physical reason? Yeah, there are some physical reasons. For example, if I want to study the propagation of magnetic field, the motion of magnetic fields in the sun, on the sun surface, on the exterior of the sun, so to speak, it's okay if we drop some of these complications. For example, what about resistivity? We may assume that our fluid, in particular a plasma, is very conductive. If it is very conductive, almost no resistivity. If there is no resistivity, i.e. eta, 0. If there is no resistivity, then Ohm's law in ideal condition becomes, you see, if this is 0, it becomes that E is equal to minus U cross B. Okay? So the first equation that we take into account is this one. Okay, better. Now we go here, we look at these equations, we have minus the curl of E, but E is minus U cross B. So we can plug this equation there, and we have the transport of the magnetic field, B, is given by curl of U cross B. Okay? No resistivity. Perfectly conducting fluid. It means that electricity is spread everywhere uniformly, and the transport of the magnetic field is given by this equation. It comes from Maxwell equation when I set eta equal 0. It simplifies. Okay, when eta is equal 0, this is the equation that relates electricity, electric field and magnetic field through the motion of the fluid, which is given by U. Sorry. Okay, it's a vector. Okay, this is known as Faraday's equation. This comes from Maxwell's equation when resistivity is 0. Then, this is the first assumption. Second assumption. Second assumption is dE dt equal to 0. The electric field, because the fluid is highly, infinitely conductive, the electricity is spread uniformly in the fluid. And so the change of electric field in time, we assume, is 0. No change of electric field in time. dE dt. Second assumption. First assumption, second assumption. If we assume this, we go back to Maxwell's equation, we are there, and you see from this we have that it's here, we have that J, the electric current, is exactly given by the curl of B. Please remember, there are some coefficients here and there, and I do not mention them. I just mention the minimum coefficients that I need. But there are some corrections in this equation, okay? But from a mathematical viewpoint, this is the second equation. The second equation is Ampère. Ampere's law. Okay? So these two equations come from Maxwell's equation, and these are the two assumptions. Do we make many more assumptions? Well, maybe one more assumption is necessary. The assumption, the third assumption that we need is that we neglect relativistic approximations or relativistic equations. What does it mean? It means that all the velocities that we take care of are at a velocity, the intensity, the modulus of these velocities much lower than the speed of light. Much lower than the speed of light means that this approach is totally classical, is not relativistic at all. And so the third assumption is that perturbation are subluminal. Subluminal. I tell you what I mean by that, technically speaking. Okay, now we are away from Maxwell equation. I can erase Maxwell equations because Maxwell's equations become these ones. Okay, so the third assumption means that I can define a velocity associated with the perturbations of the magnetic field. This velocity is defined Alphen velocity. I call it VA, and this velocity is given by intensity, so it's the modulus of the magnetic field divided by these constants, the density of the electrons, and this mu0 is called permeability of the fluid. And we assume that this velocity is much, much less than the square root of epsilon 0 mu 0, which is this, and this is the speed of light. C, speed of light. Okay? If this is the third assumption, assumptions, one, two, three, gives ideal MHD. Okay? Ideal MHD. So for ideal MHD, we have the motion of the fluid plus the contribution of the magnetic field B, and coupled with this Faraday's equation and Ampere's equation. Okay, so this is the context. We already made some simplification. Here, this is a force, right? Mass times acceleration. What kind of force should I put here if I consider magnetic fields? If I consider magnetic fields without resistivity, so in ideal condition, the force associated with the presence of magnetic field, I write it like this, just to tell you that this force should be put here, and this force depends on the magnetic field, and is given, again, I drop some constants, some physical constants, in essence, is given by J cross B. This is a force that acts on the field lines. And as a name, the name is Lorentz force. Okay. Ideal MHD means zero resistivity, a Lorentz force put in this equation, and now these equations, I call them Navier-Stokes equations with magnetic field. So I drop this, and all this become Navier-Stokes equations with Lorentz force. Still pretty complicated set of equations, but simpler because I took eta equals 0. If I include eta, then I have another term here to add. If I drop also viscosity, these terms go. So, last assumption is viscosity. Viscosity equal 0. It means that the Navier-Stokes equations become du dt equal, well, I have a rho here, rho du dt equal minus grad P plus J cross B. Okay? This defines ideal motion with the presence of B. Okay? We cannot go simpler than this. We cannot go simpler than this. This part, remember, is Euler equations for ideal fluid, no viscosity. And this part is the force due to the presence of a Lorentz type of action on the magnetic field. And that's it. That's it. Okay, so these 1, 2, and 3 give us the ideal MHD. The ideal MHD gives us Lorentz force. When I put Lorentz force, I have the motion of the fluid with magnetic fields. That is called the ideal magneto-hydrodynamics. Any question? So I think I just went through the basic equation of fluid mechanics and magnetic fields. And now I can just recall some basic properties of this ideal MHD. Basic property. So let's say fundamentals. Fundamentals of ideal MHD. From a field theoretic viewpoint. Okay? Not from a really physical viewpoint. From a more mathematical viewpoint. Okay, so we have to make an assumption on B. B. We take, first of all, remember, we take B divergence less. No divergence for B. And then we took the Lorentz force J given by the curl of B. Okay. What about B itself? Is this the break? Okay, one more thing and I'm done. B, I can write the vector field B as the curl of the potential A. And I take Coulomb gauge for A. And this is div A equals 0. I stop here. I start from the fundamentals, defining the magnetic field in terms of a vector potential A with the Coulomb gauge field div A, and I want to find a solution in terms of B due to the current J. You will see that in a... Okay. This has been done. We are now towards magnetic helicity. Okay. I still want to finish the fundamentals. Now you see, we have this and we have this. This is a kind of definition, okay? This is kind of physics. Physics and mathematics talking together. J. J is the curl of B. But B, we define B in terms of this field. What kind of field is this? Is potential. Vector potential. A vector potential. So here we have the curl of A. Okay? A physical field in terms of a potential field. We can expand this curl of a curl. Okay? So we go like this. We have the curl of a curl. So the first thing is the grad of the divergence of A, vector calculus, And this is minus the Laplace of A. We didn't do anything, nothing. We just applied vector calculus. When we applied vector calculus, we had a condition on A. We took a Coulomb gauge for A. It's just fixing a reference. For fixing a reference, now I try to say one way and then I say in another way. One way is, we take a reference for a mathematical field, potential. But now I contradict myself and I say A is not only a mathematical trick to define B, is a fundamental field. Fundamental field. Many physicists today still regard potential theory as a mathematical artifact, as a mathematical trick to compute things. And I dispute that. In my view, this is wrong. A potential field is as physical as the real field. The only problem is that when you do an experiment, you cannot measure a potential field. I give you an example, very simple. You do a theory on gravity, gravitation, and then you talk about potential, the gravitational potential. Can you measure it? No. You take the grad of the gravitational potential, the grad operator on something, and you get the force, the gravitational force. Can you measure the gravitational force? Yes. So that's why physicists don't like potential theory. They say it's a mathematical stuff. It doesn't concern physics. And I say the opposite. Modern view of physics is a taking back potential theory as a fundamental part of a physical theory. It's not only a mathematical trick. Is that clear? If you want to learn more about this, about the impact of potentials and the topology in physics, I tell you, go to read about Aharonov bomb experiment. Aharonov-Bohm experiment shows that the presence or the lack of magnetic field has an effect on the potential A, and this effect is measurable, is a measurable effect in physics. In other words, the lack or the presence of a magnetic field, what does it mean mathematically? It means that I'm going from the absence of a field, I'm talking about the domain of definition, simply connected, to the presence of a localized field, and I'm now referring or thinking to a domain multiply connected with holes. And these holes are filled by the magnetic field. And when you fill the holes with magnetic field, you have an effect on the potential, and the effect on the potential produces an effect on the physics. Okay? Right. Let's go back to this. So, because of Coulomb assumption, this is 0, and all this gives you J equal minus Laplace over A. Laplace over A equal minus J. Is this a known equation? Very well. This is called the Poisson equation. And does it have a solution? Sure, it does. We can write the J. Oh, sorry. I go back in this direction. I go back in that direction, and I can write, here it is, A, the solution to this equation that depends on the space coordinate x is written as 1 over 4 pi integral of J that depends on the sources of J, so I call it x star, divided by x minus x star mod, and this is in dV. Okay, now I have A. What is this, by the way? 1 where? Where? 1 over x minus x star is g of x star, and this g is the Green's fundamental solution. Green's fundamental solution to the Poisson equation. Okay? So this is potential theory. Potential theory. You have Poisson equation, you want to solve it, and this is the Green's fundamental solution. Green's fundamental solution is source. Not only is a mathematical solution, is a source of difficulties. Why is a source of difficulty? Oh, very simple. You see it in front of you. 1 divided by x minus x star. When x, a point, is very close to the source point at x star, there is a divergence. There is an infinity. In other words, how close can you go to the source point? If you are at the source point, something is infinitely strong. It's not physical. So it's a mathematical approach to field theory. And when you want to consider points exactly on the source points, then you have to desingularize. Desingularization techniques applied also in this context, as well as in all contexts of fundamental physics. all context. When you are on the electron, the electricity is what? Infinite. So you have to desingularize, and the desingularization is always, always, in all physical theories, is related to Green's kernel. Okay, this is Green's kernel in the integral. Okay, so we are here, but we are not there. We want J, okay? So I want to go back to J. J is the curl of B, so I have to take B is the curl of A, so I have to take the curl of the curl in order to get J. And if I want B in terms of J, what I do, this is A, so I have B. From here, I go here. B at X is the curl of this quantity. I have to take the curl of this quantity. I have to take the curl of the Green's function. And the curl operates on X, not on X star. So the curl go inside there, and I get 1 over 4 pi, 1 over 4 pi integral of the current at X star plus X minus X star divided by X minus X star cubed. Okay? And this is in dV. This equation, very important, is called Biot-Savart law. Biot-Savart law or Biot-Savart induction law. Induction law. I have a current at point X star, that induce a magnetic field B. So this is the fundamental equation that governs the relationship between J and B. Okay. All right. So we've made some progress. We are now almost ready to talk about the magnetic helicity. First, I want you to have a sense, a physical sense, an intuition, no rigorous proofs, just intuition for the moment of what we are talking about. We have magnetic field B, and the magnetic field B, I told you, can be related to A, curl of A. I want you to understand what is B and what is A in some kind of simple model. Simple model. In order to do this, I propose another context. Another context. For example, I say that vorticity, omega, is related to the curl of the velocity u. You see, there is an analogy here in front of you. What kind of analogy is? Okay, I tell you, I start from here because it's easy. It's fluids. Imagine that I have a vortex. And not a vortex general, a vortex tube. This is a vorticity. Omega. And what is velocity here? Oh, you read and you tell me. Oh, the velocity, vorticity is the curl of u. If this is a vortex, the velocity is this. This is the velocity. This is velocity. Velocity. U. Okay? We have a tornado. A tornado like this one, okay? Or, okay, you want something like this, something like this. This is velocity and this is vorticity. And this is tornado and this is the land. Okay? Big tornadoes or small tornadoes, a vortex tube, a vortex filament, all the same models for what? For this. Vorticity is localized in a tube or something like this, and velocity goes around it. Okay? This comes from, if you like, a mathematical model of nature. Vorticity in terms of velocity, velocity related to vorticity. What about this? Same thing. It's a little bit more abstract, but it's the same thing. B, we take B as a magnetic tube. Localized magnetic field. No field outside, only in the tube. So we have a tube like this, and magnetic field inside, here. And A is the potential that goes around. So this field and the curl of this field are talking to each other. Now we are moving from 100 years ago to modern time. Well, the blackboard, no change. Same thing as 150 years ago. But now we start to see things in a slightly different way. We relate B and A through this model. We relate the vorticity and velocity to this model. We start to call velocity field the potential of the vorticity. Why? Because here we call A the vector potential of the magnetic field. So the velocity that everybody knows, I can call it a potential field for vorticity. Okay, you say you change words, it's the same thing. It's the same thing, but I start to focus on this little model. I imagine that vorticity is concentrated on a tube. Follow me. I imagine that the magnetic field is concentrated on a tube. And now I look at the field lines of the vector potential as embracing the magnetic field. In other words, I see the velocity of a spinning fluid around the tornado embracing the vorticity. One related to the other. If there is a vorticity, there is a velocity field, because the curl of the velocity is vorticity. Of course, I can have a velocity field without vorticity, for sure. I'm saying now that if I have vorticity, I start from here. I assume there is vorticity. Then I regard the induced velocity associated with this vorticity. And that velocity, not other velocities, that velocity embraces the vorticity. I'm back here now. I assume that B is localized in tubes. And I'm saying that there is a relationship between B and A, not only what I wrote here. Sure, what I wrote here is a definition. I'm attaching to this definition a sense, a physical sense. I'm saying that because of these two fields, A is embracing the magnetic field. If there is a B, then I have an A that is associated with B through that mechanism. why I insist so much on this view. I insist on this view because what I'm going to tell you in a moment is related very much to this view. What view? The fact that A is linked with the magnetic field, is embracing the magnetic field. And at the end of our little course, next time, I'll show you the relationship between A and B in terms of a fundamental invariant of topology, linking number. Okay? But before that, I have to introduce you a quantity that has a physical meaning. Of course, is related to linking number. But let's leave it for the moment. And let's introduce this quantity first. Okay. This quantity, we are now in ideal condition. No resistivity. And in ideal condition, I can introduce a new quantity, now no longer new, but still not so much discussed in books, and is called magnetic helicity. H for helicity, M for magnetic. I can, I made this reference with vorticity. Let me immediately say that there is a parent, a related quantity, that is called the kinetic helicity, i.e. H of K. How do I define magnetic helicity? I define magnetic helicity as the volume integral of A dot B. How I define kinetic helicity? Exactly the same. The integral of U cross, scalar quantity with omega. Same thing. B is the curl of A, omega is the curl of U. Okay. I will forget about this quantity because I want to talk about magnetic helicity. But because what I said here, when I talk about magnetic helicity, everything can be said the same for kinetic helicity. It's the same thing. And the second thing, this is the first comment. Second comment I want to make is, remember what I said here. Imagine that the magnetic field is on a tube. A is embracing the magnetic field as U is embracing omega. What does it mean, this quantity? This quantity is a measure of this embracement, of this hug, of this linking. We will see this connection in the second part, next week. For the moment, I want to talk about this without thinking of the hug, of the linking. Okay? Okay. So, let's remove this from our mind. And let's talk about this only. Magnetic helicity is a conserved quantity of ideal MHD. Who proved conservation of magnetic helicity? Was proven by Volcher in 1958. Volcher. So we are going to prove the conservation of magnetic helicity today. Next time I will tell you something about magnetic helicity, interpretation of magnetic helicity in terms of linking, between one field and the other, and we will say something else about Ampere's law, Ampere's theorem. Ampere's theorem, the law itself I mentioned already. Okay, so, we are here. I can tell you an analogy. An analogy is if this is J, this is B, and the relationship is J equal the curl of B, and the other analogy goes like this. If this is B, this is A, and again I have that B is the curl of A, right? I can talk about J, I can talk about B, I can talk about vorticity. All these problems share the same formal analogy, one another. So I can talk about this case as embracing A with B, and you understand the same happens with U and omega or with B and J. So this is the bonus of field theory. All right, let us prove that magnetic helicity is conserved in ideal conditions. Okay. Right. Where I was here. Okay. So, due to Voltaire, we can prove conservation of helicity. We want to prove that the derivative with respect to time of Hm is 0. In other words, Hm constant of during motion. During motion. Okay, the proof is the following. Start to consider Faraday's equation. Faraday's equation is what? dB dt equal, we wrote it curl of U cross B. Okay? We start from this equation and we want A. Want A. So if we want A, uncurl Faraday's. We uncurl this equation. So we get from here, we get dA dt. We uncurl this quantity, so it's U cross B. But we must take into account a gradient term. A gradient term, I will call it the grad phi. Why? Why this? Why this? Very simple. When I go back to Faraday, because B is the curl of A, then I take the curl of A, I get B. I take the curl of U cross B, and this here. And when I take the curl of grad, this goes away. So here there is nothing, but when I uncurl it, I have to take into account the possibility of a grad phi. What is phi? It's a kind of gauge, an additional gauge. It's a scalar function, and this is a vector function here. Okay, so when we uncurl, we get to this equation. Okay, now what? Now, well, by the way, note that phi also satisfies the Poisson equation. All fields in ideal condition. So we have phi equal minus grad of u cross b. Okay, now let's go there. Now from this equation, plus the assumption that div B is equal to 0, no monopoles, so we have these two equations, this equation and this equation, we get the following: d dt of A dot B equals the divergence of phi B plus A times the curl of u cross B. Okay? Just check. I take this, I dot A with B, I have this because the divergence of B is 0, so I can take divergence of this quantity. Is given by B times the grad of phi, which is this, time plus phi times the divergence of B. But divergence of B is 0, so I have this quantity. Plus, when I do A dot B, I have this quantity to be taken into account. Now, from the expansion identity, of the curl I can write, it's a long thing, you can check yourself. I can write A dot, I'm working on that part, U curl of U cross B. Okay, there, yes. And this is divergence of, I'm just using expansion vector identity. A curl B cross U, and this becomes the divergence of A dot U times B minus A dot B times U. It's a standard vector equation. So that I finally have the total derivative. Remember, the total derivative is the sum, it's the Lagrangian derivative. The sum of the time derivative plus the space derivative. So this A dot B becomes the divergence of phi plus A dot U, and this is times B. Okay? Now, one final assumption. Remember that we take the following. Tube B, A around it. We take B, the field, with a zero component across the tubular surface. So this is n unit vector on the surface B dot n equal 0 on the magnetic surface. In other words, this is equivalent to say no magnetic flux through the surface. Okay. So now we are ready. The volume over there, this volume is the magnetic volume. V, where V, magnetic volume. Okay? So if I refer to this tube, magnetic field is inside the tube. No field through the surface of this tube. So when I integrate on the volume, I assume no magnetic flux through the magnetic surface. In other words, the magnetic surface technically is called a material surface. Okay, so now I'm ready to compute this volume integral, because I have everything. Right? So what I have is dH m dt is equal, of course, d dt of the integral of a dot b in dv, and because no flux, i.e. magnetic surface is a material surface, is material, then I can write this as a d dt of a dot b in the magnetic volume. So I can plug what I got here, the divergence, integral of the divergence of phi plus AU times B in dV. Okay? Integral of a divergence. You're doing theoretical physics, some of you more mathematical, some less. You should know, you should remember very well, I have a divergence. Under integration, I apply Gauss divergence theorem. So this is equal to the flux integral of what? Of this quantity, phi plus a dot u times b, and then it's a flux through ds, the surface, s is the boundary of the volume, and S underlined is S times the unit normal through the surface. So when I do this, I have no magnetic flux, B dot N. I replace this ds with N ds. And this is 0 through the boundary. If this is 0, this is S, and this is V, then all this is 0. So I could prove that there is no change. Hence, HM conserved in time. So this is proof of conservation of magnetic helicity in ideal conditions. It means that I can measure magnetic helicity at one time, taking information from magnetic fields on the sun, taking information of magnetic fields of stars, of planets, planet Earth. I compute this quantity over the volume of magnetic fields. Not so easy, kind of tricky, but it can be done. It is done. And once I measure this quantity at one time, say today, if we are in ideal conditions, which means that on a large scale phenomena we are, then this quantity that I measure today is the same quantity of tomorrow, of 2 days, 3 days, a week, a month, a year later. Is conserved in ideal condition. Is it conserved in plasma physics for fusion research? Not entirely. It depends. If we are with magnetic fields very, very strong, which is the aim for fusion physics, then magnetic helicity is conserved, roughly. If we have resistive effects, very important in fusion physics, which is certainly true at low temperatures, then magnetic helicity is not conserved. It means something. It means that this embracing is not the same at one time and at a later time. If we are at high resistivity, then it's not conserved. If resistivity is low, the fluid is highly conductive, the embracing is preserved in time. This has important consequences for lots of reasons. Okay, so we've proven conservation of magnetic helicity, we've proven the result of Volchi.